Good morning. We're going to start today with Chapter 19. And the way that we do is we go under the hybridplc.org website and we click on Hybrid Text. And then we go down to Chapter 19, Programming the PID Algorithm. So here we begin with an introduction, and the introduction basically points out that this is an algorithm that is put in the PLC and controls a process using a single control point and a single feedback device. And historically, the PID algorithm was not included in the PLC early on. It was put into a DCS system. DCS stands for Distributed Control System, and PLCs gradually started taking over this function, and now they're one of the best ways to do the PID function is in the PLC, and many processes have adopted the PLC as the method of choice for doing the PID algorithm. Historically, I was not involved in putting in PID algorithms. The group that I worked for in industry was a controls group, and there was an instrumentation group that was a parallel group to us, and we worked with PLCs and they worked with PID controllers, and they designed the P and ID diagrams, which stands for process and instrumentation diagrams. So they were in charge of this aspect, and we were not. They always needed a PLC, and we had the PLC working with them, but we did not do the analog work with the PID algorithms. And after I had become a teacher, I was asked by a local company to help install the PID in a process, and I accepted, and that started my experiences in this area, and gradually I became more and more, they became more and more part of the program, and something that I believe is important to teach. So I started out with the SLC from Allen Bradley, the processor that they had, and then I went to the Compact Logic processor, and I put that in, and then I also went to the Siemens 1200 processor. So I've had basically those experiences. One of the early experiences I had in industry was with Modicon, and I'll talk briefly about that, but basically, my experiences have been with the SLC, then the Compact Logics, and then the Siemens. So let's look for a minute at what we're talking about. Closed loop control is a process where the value of a variable is established and maintained continuously through intervention based on measurement of this variable. This generates a sequence of effects that take place in the closed loop control loop because the process runs based on measurement of a variable that is influenced in turn by itself. What does this really mean? Well, we're going to have to get into that, and I'll talk to you about it, but there's a diagram down here that does a much better job, and I'm going to go through this diagram with you and try to give you some ideas based on this diagram. Now, this diagram is one that's found in many, if I can get it on the screen, it's found in many control books, and it's the beginnings of looking at process control. So I'm going to come back up here, see if I can get it on the screen well. I'm going to have to come down a little bit in order to do that. So here's our PID process. This would be the process that we're going to try to control. This is a machine that is trying to produce parts, or there's trying to vary the speed of something or another, and we're using our process controller to control some aspect of it, and it's an analog system. This is an analog process. Now we're not talking about ons and offs, pieces and parts, but we're talking about flows and things that can go up and down. We'll talk about some of the projects that we have a little bit later, but this is a process. Now, many times people like to think that they can write an equation for this. It's possible maybe, but most of the time we do not know the equation for what this process is going to do. But we can use a controller to try to control this one aspect of it. And a manipulating element is nothing more than the valve, or if this is a motor, this would be a variable speed motor. So you would make the speed of the motor go up and down. If it's DC, you'd vary the armature voltage. If it's AC, you would vary the frequency. So basically, you would vary something that would turn something and make it go up and down. And this is the process that you're going to be controlling. Out from that process, you would take a variable and you would bring it back into your controller, and you would convert it from a raw signal to a signal that can be used by the controller. Sometimes this is a flow, and you would use probably the differential pressure switch, and then you would take that and you would run it through a conversion process here, which would be square root of the differential of the pressure, and you would bring that back as an analog value into the controller. Now the controller, we're going to talk to you a little bit later, has three elements, the P, the I, and the D. That's not shown in this picture, but what is shown in this picture is that the controller has two inputs. One is from the process, the feedback from the process. The other is a set point. So in other words, if you were to say, I want 60 gallons per minute of flow, this would be where you would set the 60. If you're not getting 60, this would say, hey, you're really not getting 60, you're getting 56 or 54 or 80 or whatever. But this would be the feedback, and this would be the feedback. This is your I and the process. Many times I've described this as driving down the road. I have one eye open, and that's my only sensor, but I like to drive typically with my, I like to drive a little bit to the right of center in the lane that I'm driving in. That may sound simple to some people, but if I'm on a two-lane road, I like to be as far away from the middle line as I can, so I try to drive right down the middle of the center of the road. So I position myself right in the middle of the road. That's my set point. Some people drive a little bit left of center, some people drive a little bit right of center, but basically you have a set point, and that's what your idea is of what you want. If your process says give me X gallons of fluid or whatever, or at X speed, how much of something do you want? How fast do you want to run your line? That's your set point. If they say today we want to make 800 parts, and you run your speed of your line so that we'd make 800 parts tomorrow, maybe you got orders for 1,000, you would put that speed up to 1,000. But basically this is what you want. This is what you want, and this is what you're getting. Now the difference between those two is called the error. Some places we call it the deviation, but the error is the difference between the set point and this control variable. Sometimes it's called CV or CM. Excuse me, CM, not CV. CV is the output controlled variable. CM is the measured variable. So the measured variable is the CM. It's also called the PV, or the process variable. So sometimes you see this variable called CM, sometimes you call it PV. So it's SP minus CM or SP minus PV, or it could be CM minus SP, because sometimes you have a minus sign in the system, and it could be the flip. So basically it's one or the other, but it's the difference between the two. Okay, this is your control modes. This is where you're actually going to take that information, and that's what we're going to talk about here. We're going to run it through this PID controller, and that's this part right here. And then we're going to take it and run it to the manipulated variable, and then we're going to run it out to the process, wait for the process to make some changes, and we're going to come back and do this again and again and again. Now, the old-time PID controllers were continuous. Today, we settle for something that's not continuous, but that is run on a clock. It's run either every so many milliseconds or every so many seconds. So basically, we run it at discrete intervals, and at discrete intervals, we do this process. So whether it is continuous or whether it is on a clock, it usually doesn't matter. But again, we are compromising by using a digital system instead of an analog system. Now, the example I'm going to show you right below this is an analog system because it's continuous, and I'm going to show you this here in a second here. This is a proportional only, but it kind of gives you the idea about how this can kind of work. So here we have a pressure and here we have a pressure. Now, obviously, the flow is going to have a higher pressure than downstream. We're going to force the air or the whatever, it could be liquid or air, through this valve. And the valve then can open and close. It can either go more closed or it can go more open based on this little pivot down here. Now we have a P1 and a P2. They're in a bellows. So basically, we actually here we have a bellows, one pushing against the other, P1 pushing against P2. So we have the P2, we have the P1, and this bellows can be moving up or down. Now the actual flow is related to the square root of P2 minus P1 or P1 minus P2. So it's a square root operation. We don't have a square root extractor here, but basically we just have to kind of say, well, we know that as the pressure difference is more, that this is going to push down more. It's going to push down, this is going to push up, and that's going to push this plunger more closed. Now, if we move this little fulcrum here, we can move it back and forth, and we can also change the tension on the spring. Either place will cause this system to act differently. If I move the fulcrum to the right, a little bit of action over here causes more action over here. If you're on a teeter-totter, you understand that concept because usually the long guy wins. The guy that's got the longest leg of the teeter-totter is the one that's got more leverage. So basically, the one that's, if you move this over to the right, there's a little bit of action over here, causes a lot of action over here. You move it further to the left, a lot of action over here, a little action over here. So you got the idea that there's a proportion of movement to this, and that would be the P, or the proportional term. Now, we talk about it like it's something that is, we know how it's going to work. We don't know how it's going to work. We just have to try it. So many times we see this kind of a response. Now, this is a settling in, but around a set point response. So as we change the variable from here to here, we move from down here to up here, we see this kind of a response. Now with a proportional only, which this is, we never get to the full set point. We get to a portion of the set point, which is some offset from the set point. That's a fallacy of the proportional only controller. The P controller has that fallacy, but we accept that to an extent, but we then go ahead and say, well, for real good accuracy, now obviously if this is my real set point, I can lie and say move the set point up here when it's really down here, and I've got a good set point with just a P controller. I understand that, but that's not what we're about. We want to say I want to make my set point, and I want it to go up to that and then stabilize there and be a good set point there. So that's what we want. Even though we could, we could lie and say, set it up here, but this is our real set point, so it's good. We don't have to worry about it. But what we do is we add another component called the I. Now the I component takes the integral of the error, and then it takes that integral of the error over time. So what does the integral mean? Well, the integral is the summation over time. So as the error here happens, you see the output actually, based on the I controller, it increases. When the error goes to 0, it just stays where it was because it had built up to this point. Now, when it's down below 0, or the error is negative, it starts to decrease. So it's the summation over time. So when I first started out in my job, I had no dollars. But over time, I gradually, by saving 10% of my whatever, I gradually built up my nest egg, and then when I wasn't saving anything, I didn't have anything, and then started borrowing from it. I started taking money out of my savings account. So basically, this is kind of like your checkbook or that type of thing. And as you have needs, you take it out and you put it back in, whatever. So that's what we have there. Okay. So down here is the proportional and integral controller set up in the controller. This is the P and the I. So this is the P and the I controller, and putting the two together, we have an error, and then we have over time, we have from a baseline, we have going up, and then when it goes to 0, we have the proportional term coming down, and then we have it here, we have it going down again, because the proportional term is just a number times the error. So that's this part. When it jumps from here to here, that's the error part. This is the proportional part. Here is the integral part as it climbs. Here, when it jumps, that is the proportional term. And then here is, again, flatlining, no error. There's no integral of the error. And then it jumps down, and then it comes back down over time, because this is the integral part here that's working over time. It's the slope. The proportional term moves fast. The integral term moves a little slower, and that's by design. Now, the differential part, again, very rarely used. The D term is very rarely used, but it is used in one of our labs called the ball and tube lab. And in that case, we have to use the D term or it will not work. It works very well with the D term in. Okay, so here is the P, the I, and the D. The P term is a proportional term. The integral term is this term right here. And as you can tell, the D term is when it jumps up, it goes way high, and then it comes back down. So you see these little curls in if it's a step term like this, you see these little time delay terms that go up and then go back down and that type of thing. That's the D term, and very rarely is it ever used. This is an equation, and this is pretty much the standard block equation that you should know what's going on, because this is the K term, the I term, and the D term. So the KP term is a number times the error. The KI term is a number times the integral of the error, and the KD term is a number times the derivative of the error. We're going to go through an example in a little bit that shows you how to kind of get an idea about how this works. Okay, so here is an example of the P and the I, not the D, but just the P and the I. So here we start out with the output. It's at a certain point. The error jumps up at this point, and at this point, we start with the integral of the error. So basically, at this point in time, we start moving up. The output starts moving up. At this point, it moves up faster, and we're going to go down through here, and we're going to actually look at the what actually is going on here. Okay, so this is the one we want to look at right here. Error is 0. The output is floating along at some variable. We don't know what that number is, but it's floating along there, just kind of holding its own. Now, at this point in time, the error jumps up. Now, this part here is jumping up because of the proportional mode. This part here is jumping up because of the integral. So over time, it's the time, which is in the x-axis, times the height, which is in the y-axis of the error. So it's the x times the y. So it's the area under this curve that actually builds up. So over here, where we've gotten more output, we've gone from here to here. So the summation of the x times the y under this, in this rectangle, is the value that we end up with over here. So we start here, the integral of the error, and then we end up over here. Now we jump down because, at this point in time, because the error goes back to 0. So the proportional term causes this jump right here. We stay at that error variable, until we come to here, and at that point in time we jump down again because the proportional term turns to jump down. After that we start going down because the integral of the error, this is under the summation of this box takes us to, at some point in time over here, it takes us from this point to this point down, and that's the integral of the error causes this slope to happen like that. Okay, so let's put numbers to this. In this case, we have a proportional term. We assign it. This is called a tuning variable. P, proportional term, is 2. The 1 over the Tn term, or the integral term, the integral constant, is 0.02, and the beginning point is V0. In other words, that's where we started. That's our baseline. So we use the equation instead of just the P term and then the I term. We say, in this case, we say, and sometimes this is the way it's done. Sometimes you have to be careful because sometimes this term is two variables, sometimes it is one variable. But in this case, for this example, we're saying this term here is the P times the I term. So it's this times this times this. In other words, it's this variable times this variable is entered here. So basically, for the I term, it's the P term times the 1 over T term, okay? So that's where we start. Now at 0, we want to find out what the value of the output is. So it is, what is the error? Well, the error is 0, and then it's 2 times 0.02 times integral from 0 to 0. What's the integral from 0 to 0? It's 0. So basically there is nothing. So we don't go off of 32. This is our constant, so we're at 32. Then we look at 20. So we look at 20 seconds, okay? Now at t equals 20, look what happens. We jump. We go 2 times 10 is 20, plus the integral of the error, which is, up until that time, it was 0. So the integral of the error up until that time was 0. So it doesn't affect us, but we have the 20 plus the 0 plus the 32 is 52. So at t equals 20, we jump to, our output jumps to 52. Now what happens at 70? Well, at 70, we have time where we build up the integral of the error. So at 70, we've still got our error at 10. So it's 2 times 10, or 20, plus 2 times 0.02 times the integral from 0 to 70 of the error, which is time. The time from 20 to 70 is that number. So it's from 20 to 70 is 50. So 2 times 0.02 times 50 is what? It's 72, because 2 times 0.02 times 50 times 10, which is our error, is 20. So that gives us 52 plus 20, or 72. So at that point in time, at 70, we've climbed to a value of 72. Now you can complete this and go over here and start calculating the error even further. And at the end of this chapter, there is an example for you to practice on as well. But basically, this gives you an idea how this PID controller works. And as you're looking at a PID controller, remember this equation. This is what's happening. And every time you come through and execute this equation, you're actually doing this little piece right here. So that helps, hopefully, understanding what you're actually looking at and seeing. So it's the P term times the 1 over T term times the amount of time times the actual error itself. And that gives us 20. And that adds to the 52. And that gives us a variable 72. Okay? And that shows us here, 52 to 72. And then at this point, it jumps back down and it starts going back down. You can finish this off. So when I was first teaching, a fellow called me and asked me to work with him on a project, and it was to make dog food. And we went through, and he had already done most of it, but he wanted to add an ingredient, and that was the fat. So basically he had an SLC processor, and we wanted to add the fat. And it followed a process that already was in place where they added the other ingredients, and then they turned an extruder with a motor, a big DC motor, and out came what I call kibbles and bits. So basically this was already in place. They just wanted to add this one ingredient. Now, missing from this picture is the flow transmitter right in front of this valve. The flow transmitter was the feedback device. So right in front of the valve, we had a little transmitter that said what the flow was coming from this vat. And you say, what did fat look like? It looked about like this color, and I don't know for sure what variety of fat it was, but it was a liquid flowing out and coming down in and going into the extruder. And they wanted to vary the percent of fat in the extruder by percent. So if the motor went faster, you would get more. If it went slower, you would get less. And they wanted 2%, 3%, 4%, 5% of the output to be from this variable right here. So there was two things going on. You could set up the percentage of fat in a batch or in the process, and it would also follow the motor speed. So as the motor speed went faster, you would get more. If it's 2%, but you're running at 1,000, you'd get more than if you were running 3%, you're running at 200. So you would be basically controlled, this valve would be controlled by a set point plus this motor speed. So that was how this was supposed to run. So this kind of picture shows you how most processes are set up. They're set up with a master, and then you have your various rates coming in, and all of the various ingredients that were going into that extruder had a rate that they were coming in at. They were being fed in by some kind of a feeder, and they were coming in based on some kind of a set point and the master motor speed of the extruder drive. So as you cranked it up, let's say we got an order today for 1,000 bags. Well, if you had 1,000 bags, you want to go pretty fast. So you'd crank your motor speed up to give you 1,000 bags. If you had an order today for 400 bags, you'd turn your speed back down, so it would be a little bit less, and you would not be running as fast. Or maybe you'd run at 1,000, get done earlier. But whatever it is, you have the choice of running this whole line faster or slower based on the motor speed of the extruder motor. And that's the way it should be. If you want to make a little bit more, you turn it up. If you want to make a little bit less, you turn it down. And you have one master speed that feeds the whole line. So we call this a control system, and there are modes involved with the PID algorithm. And I think you probably should be able to see that, because in order to get this thing started up, we had to have, and I'm going to shrink this down just a little bit, we had to have different modes, and I had to come up with these modes kind of on my own, but I saw them as part of this process, and as I was reading through, I figured them out pretty well. But we had to have something like this, and most of the processes that we do, we have to do something like this. So the CV is the output. That's the output that goes to the valve. So in this case, we had in manual, you had to do that because you wanted to be able to turn the valve before we ever started this process up to be able to see what our flow was to test the flow transmitter. So we would turn the valve to 60% or 80% and see what the flow was to see if the valve was working properly and see if it was calibrated correctly. So in order to do a proper calibration, we had to do this. We had to go in manual to a certain percentage on, go to 100%, go to 50%, go to 75%, and see what the calibration was. So we had to be able to do that in order to test the calibration of the flow. In order to get, okay, now our flow transmitter is telling us we're getting 50 when we're actually getting 30. you have to make a calibration change in order to get this to work. So you had to be able to do this to get your flow transmitter to be calibrated to be working properly. That's why this is important. Manual is important to be able to turn that valve to a position and guarantee that it stays there. What you're doing in manual is you're ignoring the P, the I, and the D algorithm, and you're basically just coming in and saying, I don't care what the P, the I, and the D is. I'm going to go around that, and I'm going to turn that valve to a certain position, to a certain percent output. Now in auto, we had to tune these variables, the P, the I, and the D. We had to come up with the variables that went along with that. And we had to come up with those variables in some way that was not including when we're actually running the process. So we had to tune the algorithm. We had to make sure that those P, the I, and the D variables are what we want them to be. And you say, how do you know what they are? Well, some people know by experience what those variables are. There are tuning algorithms, and I do not get into the tuning algorithms in this chapter, but you can read up on them, and there are various tuning algorithms that you can use. Another way of doing it is with the Siemens is to just hit auto tune, and they will try to tune it themselves using a process that they have inside the PLC. Now, auto tune is not available in some of the Allen Bradley units. I don't know if it's available in some of the more expensive units, but it is not available in the units that I had when I was trying to do this. So I had to guess. And I guessed pretty good on the P term, but on the I term, I thought it would be better if I made that TN term big. And I made it as big as I thought it should be. He said maximum is 25. Well, I thought that would make it go faster. It made it go slower, and I didn't realize that. And at this point in time, I never had done one of these before, and I basically phoned a friend, and I said, Alan, what do I do? He said, well, I think in that case that the TN term, it's the reciprocal, and bigger is slower, and small is faster. So I looked, and the minimum value is 0.2, put in 0.2, and the thing came right up to speed and was very responsive from that point on. So my P term worked. My I term, I had to go to the other extreme. Instead of 25, I went to the small term of 0.2, and it worked. It worked very, 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 very well. And then I was able to go to the remote mode and turn it on with the following of the motor speed, and then basically have a percent of the motor speed, do my P, the I, and basically crank out an output. So again, you don't get there immediately. You have to do all three modes. So all your PID algorithms have to have all of these in order to work. Sometimes you do not have a remote mode. Sometimes you only have a local set point, but you have to have this ability to go into manual and try to turn that valve. Now, maybe you don't want to let the operator or the person on the floor do this. Maybe this is a maintenance person, but you have to have that ability. This whole product, part of this thing right here, can be done many times with a setup screen. And the setup screen is available in all of the PLCs that we have. The Allen Bradley and the Siemens both have what we call a setup screen. I'm going to show you that in a minute. But with this one, you had to be able to do that. So here we are. We have this extruder, and we were setting it up. And I discovered all PLC programs have to have these capabilities. They have to be able to get the process variable or the CM term in and scaled. You have to run your PID block, and then you have to turn on that output. So you have to do all three of these things. Now, in the later versions of the Allen Bradley, this scaling and this scaling was done when you configured your I/O card, but it still had to have this one. So whether or not you had to have all three of these or just this one, you still had to do this process by scaling your input card and by scaling your output card. So whether you have to do this inside the PLC, Siemens makes you do this inside the PLC and this inside the PLC, or whether you do it when you're scaling your input card and your output card, you have to do it. So here was the first one. Scale the input, do the PID, scale the output. Now, where is the auto in the manual? I didn't have it yet, but this is the beginnings. So I had the auto manual just by being able to click on this screen and be able to set it up through the screens. But at least I had the ability to do that. Okay, so in the, I discovered as well that there was a scaling effect, and you had to be able to scale the number. You had to look at what the variable coming in was, and you had to be able to scale it. So in this case, I was using a 420 milliamp input card for my input, for my process variable. And that number that was coming in varied from 3277 to 16384. And you'd say, well, how did you find that out? Well, I looked in the Alan Bradley books, and I put these variables into this table because I wanted to see that these numbers are important, and they come from the input cards. So basically, they tell you the number. So if you have a 0 to 5 volt card, it's this number. If you have a 1 to 5 volt card, it's this number. And you can see these look a lot alike because 1 to 5 volts and 420 milliamps both have the same scaling factor, and they're built the same way. But you have to know these numbers, the 3277 and the 16384. Now, where these go is into the scaling with parameters, in this case, instruction. Scaling with parameters is nothing more than a calculation of the old expression y equals mx plus b. So basically, they're giving you the input of that, and then the scaled min and the scaled max would be my actual numbers. Now down here, I would have to pick numbers that would be my scaled variables, like 0 to 1,000 or whatever. So 1,000 is my high number. I would have 0 for the min and 1,000 for the max. Usually, the min is 0. Usually, the max is the maximum number. Now, in cases of integer math, you really can't let, like, if it's 90 gallons per minute, you don't want to use 90 because you only have from 0 to 90, so you only have one part in 90 parts to control. So what you want to do is with integer, you want to say, well, instead of 90, I'm going to say 9,000. So it would be like an implied decimal point you would have your number in hundreds of gallons or something like that. But that's the difference between integer and floating point PID blocks. With an integer, you have to have an implied decimal point someplace. With floating point, you can say 90, but you have as many decimals to the right as you need. You have seven decimal places. So you basically, with floating point, you don't have to worry about this scaling thing. But with integers, you do. You have to remember all this stuff in your head, or you have to write it down someplace. So integers are not good. Integer floating point or integer PID is not good. But that's for quite a while. That's all we had, so we had to do it. With scaling with parameters is important because you have to get these numbers in, and you have to scale them to something meaningful. That's why this is shown. Then you take that process variable and you move it down to the process variable in the PID block. So that's your move. And then you take and calculate it, and then you take your control variable and you move it to your output to move that back into your valve the same way that you did the input in, and you have to convert that to a number that's meaningful. In this case, the number is from 6242 to 31208. You say, how did you find those two numbers? Well, again, I looked in the book. That's why it's important to have the instruction book from your input card and your output card there. Those input and output cards also have an accuracy, a quoted accuracy, and they also have an update time. And how often do they update? They have to update frequently, because if you don't have a quick update and you're taking variables that are not fresh, that are maybe 20, 30 milliseconds old, your calculations are based on information that was 20, 30 milliseconds, maybe 50 milliseconds delayed, and they're not as good as if they were information that you just had recently, like within the last couple of milliseconds. You want fresh and updated information, and that's why it's important to configure these cards correctly. And with the Siemens especially, we don't worry about that because all of the data is immediate. But when you have cards stacked up, and in all systems you're going to have those cards stacked up, you have to worry about that aspect of how fresh is the data, how pertinent is the data, and it has to be because you're going to run this on a clock. You're going to run it every 100 milliseconds, every 10 milliseconds, every second, something like that. But you're going to run it on a clock, and you want fresh data. The old rule of thumb is you want it within at least 10% of when you're running it, because if it's 100 milliseconds, you want it in the last 10 milliseconds. You want it fresh. You want it up to date, or else your algorithm isn't going to be very accurate. Wiring is important, And being able to wire an input and an output is extremely important. So basically what you have is, an input especially, you have a 24-volt DC supply, not grounded, and it goes to your analog input. There's a transmitter up here. And that transmitter is a device that borrows voltage from the 24 volts, like 6 volts or something like that. And it converts the information that it's seeing from the field into a signal that outputs 4 to 20 milliamps. So basically it's borrowing voltage and then it's outputting from 4 to 20 milliamps to the PLC input. So on a 2-wire system, you use 2 wires to go out there and you bring this back, and you have on that 2-wire system, you have a 4 to 20 milliamp signal that's using unshielded twisted pair wire in a separate conduit. And when you bring these back to your PLC, you do not land them on terminal blocks. You put them straight into the input of the PLC. So that's important that you do that, and always keep your DC wiring or your analog wiring away from your AC wiring or your 110 or your motors, especially your motors. And then the output, the same way, but you have to be careful in the output whether the 24 volts is included or not. Please read this, because most of the time it is not. It's implied, it's in the output itself. The PLC output carries the 24 volts with it. I've done it where I've wired it up with the 24 volts and I smoked my output. So please read the output to figure out whether or not you need to supply voltage or not. Most of the time you don't. Some of the times you do. You have to read and see whether or not you need that. And that goes to the 4 to 20 volt milliamp to the output, the control valve, or it might go to a variable speed motor. Whatever it goes to, this is a signal that can vary. It's an analog signal that can vary. The inputs and the outputs that are not used are typically jumpered out. Again, read the instructions for the specific book or the specific card that you're dealing with, because many times you have to jumper them out. All right, so inside of the PLC, what do you see? Well, basically you see this block right here, and you get a sequence of instructions, internal words, a listing of words, and they all have this. And then you have to set up the system of words. So you say, oh my goodness, look at all these things I have to do. You don't have to do them all. You have to do a few of them. Now the AM stands for auto manual. So basically, if this is a 1, it's in manual. If it's a 0, it's in auto. So you set this bit, whether you want to go in auto or manual. So there's your auto manual. The CM is the bit that says whether or not it's a SP minus PV or PV minus SP. In other words, it's the minus sign in. And how do you know? Well, if the CM, if you turn it to auto and it goes to full on, full 100%, or it goes to 0%, one of those two, if it does that, if it drifts off like that, you got a minus sign problem. So you got to change the bit. Just flip the bit. And if you flip the bit, usually you'll find that your algorithm will work, and it will turn on and work correctly. I've not had this very many times, but in a few times that I have, I said immediately change the CM bit, and it worked. So basically, this is one where you have to put it to a 0, leave it as a 0, unless your output goes to 100% or 0%. And in that case, put it to a 1. Flip the negative sign, flip the sign to a negative, and away you go. These are your 3 PV, or your PID algorithm. Excuse me, your gain, your reset, and your rate. These are your 3 ones you have to find yourself. See, how do I know what to do with these? Well, again, the tuning parameters in the Siemens, they're handled with the automatic tuning. On Allen Bradley, you have to kind of have a little bit of an idea, and we're going to go through a couple of these a little bit later, but very often you put the rate, the TD to 0, and you just settle for the KC and the TI. The set point is a variable that's coming in from the outside, whether it's the local one or the remote one. You have to figure that out, but you have to figure out that, in this case, separately from this block. And some of these are internal values that you don't have to worry about. Some of them you have to set, like the output max and min, you have to set that. But you know that from configuring the card. Okay, so again, we go through this and we talk a little bit about the numbers and where they end up, but basically that settles this issue of that. Now here, is this PID setup. So when you're looking at the PID instruction in the upper right-hand corner, always in the upper right-hand corner, there is this little box or two boxes that you click and you get to this setup screen. They all have it. Allen Bradley and Siemens both have this setup screen. So basically here is where you start. And if I wanted to say, I don't want the operator to ever be able to go to manual, well, you use the setup screen to go to manual, and you push this to a 1, and now you're in manual, and at that point in time, you can turn the output, the CV, to whatever you want. You can turn that valve to any position you want. You say, well, I don't want the operator to ever have to go to manual or ever be able to turn on manual, so I'm not going to program it. That's fine, but you can use the setup screen to do it during the setup, and you can have your maintenance people trained to be able to use this screen to be able to do it again. So you can use this screen instead of having an HMI screen to do this, or you can have this all on an HMI screen, but right here it's given to you to be able to get started. This is your startup. It's where you find your P, your I, and your D, and the loop update time. Now here, the loop update time is set up in this program so that this only runs every 1/10 of a second. Now you can set it up that way, or you can have it in a separate program, in a separate interrupt-driven program, and I would recommend that you put that into a separate interrupt-driven program. That would be the best way to do it instead of doing it like this. But you can do it any of a number of ways. This was the old way of doing it, but again, I would set it up in like a OB30 with a OB30 for Siemens would be the preferred way, and that would be my suggestion. Here is my control mode, and this is E equals SP minus PV. You click on it and you make a change, it'd be PV minus SP. And this gives you some ideas for the reference manuals. Again, your reference manuals are your best friend. And this gives you some ideas of how to change things in your startup screen. Very powerful. So the simple PID algorithm from the SLC processor demonstrates many important steps in implementing the PID block successfully. First, the input must be correctly signal conditioned, and the output must be signal conditioned as well. The wiring must be correct, so you have to do all that. You have to do that first. The PID block must be configured correctly, including all min and max values plus all tuning parameters. Then the engineer can control the program either in manual or auto from the program help menu. The PID block must be placed in a block that executes on a clocked interrupt, or a PID block itself must be programmed to execute on a timer in the main or OB1 block. Either method works, but is preferred method to use a separate timed interrupt block. Also, the data must be guaranteed to be fresh. That is, the data must be from an algorithm must be gathered recently. This must be as recent as immediately read from a scanned card that reports, or from a scanned card that reports to the main CPU on a regular basis. This is extremely important. This data must be guaranteed to have been read in less than 10% of the time since the last execution. This is a rule of thumb of less of 10%. So you, again, the quicker that you get that data, the fresher the data, the better your algorithm is going to be, and the better it's going to perform. Okay, and we have a picture here of some faceplates. So these are PID controllers that are dedicated controllers from various manufacturers. On the left is one from a company called Red Lion, and on the right are two different ones from Honeywell Corporation. Now these have two parts to them, basically. They have the controller and they have the operator interface, which is called a faceplate. And the reason for showing you these is these faceplates are the way that these manufacturers want you to get the information in, or the operator to get the information in. So this would be something that would be placed out where the operator could get access to, and they can then put these numbers in and change the set point, and look at the variables that are involved, and they can maybe make some updates as well, and maybe with the P and the I and the D. So again, these are standalone controllers. They would be in a control panel, and what we're doing is basically replacing these. So you have to do both the replacing of the inside, which is the PID algorithm, which is the instruction that we've just been talking about, and you also have to replace what the operator sees, which is this part right here. After that first experience, I was asked to work with a company, and that was a case where I was actually taking the Allen Bradley algorithms and moving them to Modicon. And I don't show that here, but I do want to show you kind of what they were doing. So you say, how can you get more complicated with these PID algorithms? Well, basically they were using them to turn on the gas and the air. In that case, they were using oxygen to control burners that controlled the heat in a glass furnace. So they basically were heating glass to 2200 degrees Fahrenheit, 2100 degrees Fahrenheit, somewhere in there, with PID controllers, just exactly the way that we described them above. But they were, instead of integer PID controllers, they were floating point floating point controllers. And how did they do that? Well, they did it through zones, and each zone consisted of this kind of an arrangement. You had a temperature controller, which said, give me 2100 degrees. That was a set point. It had a thermocouple that came from the inside. The thermocouple was a feedback device that said what the actual temperature was. So you had a thermocouple and you had a set point. You say, I want to heat to 2100 degrees. Well, the output of that was a number from 0 to 1000 or whatever, really a 0 to 2100 or whatever, but it was a number that was not in degrees. It was in BTUs per unit. In other words, the output of this was in BTUs per unit of time. And then how much gas did it take to make that many BTUs was how open the gas was. And there's also one for the oxygen. So basically, you had these two controllers running side by side. Did they run together? No, they didn't. And they could be tuned separately, but I don't think they were. I did not tune them, but basically I wrote the code to do this. So here we have set points coming in, process variable, and this was the control of how you heated a zone. And this is how it's done in most applications, because this company did this throughout the world, and basically they were the heart and soul of how you did control of temperature in glass furnaces. This is exactly how it was done. So more complicated. Each of these controllers had to have auto and manual, set point, process variable, output, and all the stuff you had to put on some kind of a page restricted or whatever. It's more complicated, but yet that's exactly how it was done. So I learned at that point in time, this was the basic faceplate that they used on all their controllers. And it was a faceplate that didn't look like this as much as it did some of the ones that I'm going to show you later, but it had the functionality of this, and it was a more complicated faceplate than some of the ones that we do show you later. That you had a bar graph that was for the set point, a bar graph that was for process variable, a bar graph for the output. You also had the ability to enter the set point or enter the output. If it was in manual, you could directly enter the output and put that number in here. If you were in manual, you could also go up here and click 5% or 1% of downward motion, or 1% or 5% of upward motion. In other words, you could quickly augment or change this output by 1% or 5% at a time. You click this 5 times, it's 25%. Same way over here, I could enter the set point directly, or I could juggle a set point by just clicking on this right here. This would be 1% or 5% down, 1% or 5% up. Now these little triangles are not necessary, but they really do make it easier for somebody to change the set point, or in manual mode to change the output direct. This was the going from auto to manual. This was going from local to cascade. So I wanted to talk a little bit about how the philosophy was in that program to do all this control. And basically, you wanted to be able to do everything in the cascade or the controlled mode that I just showed you. But if in cases that something were to go wrong, you fell back to another mode that was less dangerous. So your best mode was remote auto. Your next best mode was local auto, and then you ultimately fell back to local or manual. So you wanted to do whatever it took in order to get that. Now here's one of the things that they did. let me go back okay, so in the input, to the temperature controller, you had one input, one I, but they wanted to hedge their bets. So basically they had a number. I think they really had 5, but I just showed 3 here. But 3 temperature controllers, or 3, not controllers, but 3 thermocouples coming in. So we'd have thermocouple 1, thermocouple 2, thermocouple 3. And they wanted to do an average of those 3. So how do you do an average? Well, one way of doing an average is say, I wanted to take a weighting of the first thermocouple plus a weighting of the second thermocouple plus a weighting of the third thermocouple and add them together. But if for some odd reason the person doing these averaging or these weightings did not come up to 100%, what did you do? Well, you have to do something. So basically what they did was they threw it back to manual. So in the program, we had, if these 3 numbers didn't add up to 100, you put the system back in the manual, and you force them, give them an error, and tell them, hey, you got to put up 100%, or else you're in manual mode, sir. You got to get back and put these numbers to 100%. So they could jockey around with these, and in manual mode, the valve stayed in its last position. In other words, everything just stayed as is until they got the thing corrected. But they'd sound the alarm, somebody would come in and fix it, and then they would make sure these numbers added to 100%. It's interesting to note that different people, different shifts ran these with different numbers. And I thought that was kind of interesting because somebody ought to come in and say, well, this is the right way to run it, and that was it. But no, everybody had a little bit different idea of how they were going to do their process for their particular shift. And they did. Obviously, if one of the thermocouples went bad, and you could see that it went bad, you would take it out of the equation and then fix it and then put it back in. So this gives you the ability to quickly get back up and running and then fix the problem and then get back after that and put it back in. That gives you a little bit of an idea. What kind of programming is there involved? Well, there's a lot, because this is a process where you're actually looking for things that can go wrong and then shifting back to a mode that is safe. And then when you get the thing fixed, then you go back to the better mode. So here's an example of when you turn a valve, okay, and the valve doesn't turn. This would be a fault. And what you want to do in that case is, if you have that fault, you want to be able to stay with the output at that particular point and not go to full on or full off. So basically what you do is you go to manual. In manual mode, in that case, you stay at that position. Your valve stays in that exact position. It does not start to go higher or go lower because you get an error. And one of those is, I use as a rag in the valve. In other words, if you get a rag in the valve, you've got to do something. You've got to detect it, and you've got to go to manual mode and stick the valve at the last position and then tell them, hey, you got to fix this, or else something's going to go wrong. What happens if that error continues to persist and you're in auto? Well, you get a term called wind up. Wind up is the accumulation of that error. You remember, after a while, the error starts to, if the error persists, that the accumulated value of the output starts to go, and it keeps going, and it keeps going, and it keeps going. These things can happen, and they can go to 100%. And it takes a while after you fix the problem for them to come back to zero, or the error to resolve itself. That's called wind up. And you do not want that to happen, because it takes forever for those valves to go back to where they should be. So what you do in the program is you write a program that tells you to go to manual, and usually then you, at that point in time, the integral of the error term is zeroed out. This is done automatically for you. You don't have to do this. It's zeroed out. The integral of the error term goes to 0 if you go to manual. And that's on purpose, because what you want to do is you want to let the operator fix the problem and then go back to manual, or go back to auto, and that's what he does. At that point in time, your integral of your error term starts working again, but in the meantime, you've not damaged your equipment, you've not gone to 100% or 0%, or had the analog system set there in some bad state for quite a while, because the integral of the error term takes a while, it persists, and the integral of the error term takes a while to resolve. So you want it to go to manual, go back to auto after the problem is resolved. Okay, those are the two main ones. I also did a steel furnace. I did 2 steel furnaces, and I also did a glass furnace for a company that basically was making a green process. But we want to talk to you about processes in the lab as well. So I started working on processes in the lab. And the first one was the valve on the wall, which we bought a valve and a flow transmitter. We put in, and it was good for 0 to 90 gallons of water a minute. That's a lot of water. And it was flow down a drain, and it worked very, very, very well. The problem with this was that our drain plugged, and we've never been able to resolve that issue. And so we had to stop this lab. It's a very good lab, and I show you the equipment here and how much it costs, and I show you a picture of that valve on the wall, and I look at it and I think, well, if we ever get a chance to fix the drainage issues, we should be able to get this back and running. Now, this required instrument error, and one of the problems that we had was the instrument error that we had water in it. And again, if you have bad instrument error, you will mess these valves up royally, and water is a killer to these guys. So water in this line right here, this is supposed to be dry air, and if it's not, it'll mess these guys up royal, and it did. But there's our flow transmitter. That's a little flow transmitter, and there's our valve. Here's a picture of the flow transmitter. Nothing more than a little paddle wheel at the end of a rod, and it basically sits there and gives us pulses. Those pulses are turned into 4 to 20 milliamp signals, and away we go. It also had a nice little graphic output that showed us what the flow was. It was calibrated. When we brought it out of the box, it was already calibrated. We didn't have to do a thing with it. And we had analog, and that we used for that flow, we used the compact logic processor, and we bought the compact IO, and we bought the combo card with in and out, and it had 4 in and 2 out, and we calibrated those, and away we went. And this is the way we did it: flow transmitter and flow valve. We wired it all onto one card, and it worked. This is the setup of the card, and this was the clicking on that little box configuration, and this is what you got when you clicked on the little box. A bunch of tabs, but it wasn't that bad. It's not, and I go through and show you some of the setups, but you can see from this that it's not that bad. These are very, very useful, and again, I recommend you very much that if you have the time and to look through this, and if you ever get it in the real world, you can set this up, and it works very, 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 very well. This gives you an example of a compact logics analog system with PID control, and it works very, 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 very well. The setup is right here. Again, you have to guarantee the I/O update is quicker than the update of that you're reading in the PLC for your PID loop. You got to get it quick. Calibration is done at the card level. Look at this. The signals are done there. And again, this is the listing of all the variables inside the PID algorithm. You have to set up some of them. You don't have to set up all of them, but there's some there that you have to definitely set up. There's my tuning parameters, 0.4, 1, and 0. So those are my 3 tuning parameters for water. Now you say, does this matter? Well, in this case it did, because if I took this number 0.4 for the proportional term and went over 1, 1.2 especially, anything above 1.2, this thing went stark raving mad. So you change the set point, and it would go unstable. It would go full on, full off, full on, full off, full on, full off. So just moving that 0.4 up to 1.2 caused that thing to go unstable. Anything over 1 caused it to go unstable. If you moved it past 0.8, it would start to drift. But 1.2 and the thing went totally nuts. Yes, those numbers mean something. Okay, so here we are setting it up, the P, the I, and the D. We just had to, you say, how do you know that? Well, it's go fish. And we had to do that for many of these variables, but it was not hard. It was very easy, knowing the D term is 0, and you start putting in numbers until you got it to work, and it worked. Very, 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 very easy, but again, you have to do that. Or you have to go through an automated tuning process, or you have to use some other process to look at it. But again, I cannot say it too much that usually using common sense and knowing kind of where the tuning parameters are, you'll get it, and you'll get it very quickly. You'll see that it's either too slow or too sluggish or it's unstable. It's either too sluggish or it's unstable or it's okay. Okay, so these are signals that are coming in to the PID algorithm for the water valve on the wall. Sorry that this does not work for us anymore. This is a very good lab, and highly recommended that you spend the money and if you have the money, it's a good lab. If you have a good drain, this is a good lab. We do not, so we had to kind of curtail this one. You also need good air, and my recommendation there is, instead of having air coming in from an unknown supply, put your own little compressor in and have a compressor local to you that you can use, that you can eyeball, that you know is dry, because if somebody else moves the air supply around and doesn't put a dryer in, it'll get wet, and that's not good. So here is a faceplate. This is a faceplate, and the animation of these arrows going up and down is important, and you can do that. And this is one of the things that the factory talk logic allows you to do. Now, with the newer Allen Bradley HMI and with the Siemens HMI, they don't give you a faceplate like this to start with. You have to build them yourself. But again, this one does not have little triangles on the side. You would have to put those in yourself. Those are good to put those in, and I would recommend them. But here would be a generic faceplate that you could start with and start building from. The animation of the faceplate is the animation of those arrows. Okay, this is telling you some of the other variables you have to set. I very rarely did anything with deadband. I ignored it. You might think that you would need to put in some deadband, but you're going to make those decisions yourself. So here is the HMI on the screen, looking at it, and the animation, setting it up, using the connecting of the variables, the animation part of it. Now I come back and I talk about additional items that have significance here. So I showed you a complicated process with the single zone of a furnace, a glass furnace. But now physically, you don't always have ideal conditions. And one of them is with a steel furnace. You have to know some chemistry, or somebody has to tell you this. They have this idea of cross-limiting. And I was told this idea of cross-limiting, and they used that word a lot, and I had no idea what they meant. But I was supposed to program a steel furnace to do the same thing that the glass furnaces have done. Well, we use cross-limiting. What does that mean? Well, I found in a book a picture like this, and it basically identified that, and it basically told me that I had to put something in called a lag block. Now, what does a lag block do? Well, it basically lags a signal for a number of seconds. So I have a variable coming in for my temperature, and I have to lag one of them. So which one do you lag and why? Well, picture with gas and air, not oxygen, but air. There's a 9.1 ratio between the amount of gas you put in and the amount of air you put in. So there's 9.1 parts of air to 1.1 part of natural gas. So what happens chemically if that ratio is upset? If you're going 9.2, Well, you're a little bit off, but not much. 9.2 is not bad. 9.3 is you're a little lean on the natural gas, so you don't burn quite as efficiently. The more lean you get, the less efficient you get. The more air you're putting through, you don't need. However, if you get to 9.0 or 9.0 or 8.9 or 8.8, what happens? Well, the excess gas pools. If you're at 2100 degrees Fahrenheit, that excess gas burns off. It just goes up the chimney. But if you are at 8.9 or 9.0 and you're in a steel furnace and you're running at less than the temperature at which natural gas burns off, your natural gas pools. And guess what happens when that happens? It blows up. So you have an explosion inside the furnace, and it tears things up, and you have to fix things, and you have a fire. So that's not good. So this lag block lags the signal and allows you to pick as you're moving up or down in temperature, so that you're always guaranteeing a little bit higher than 9.1 or 9.1. Gas is always the low, oxygen is always the high. So the lag block allows, if you're moving to a higher temperature and you're opening things up, it allows the air to move faster, to make it a little bit 9.2, 9.3 until it stabilizes again. And if you're moving down, closing things down, you want your gas to move first and your air to move last, so that you're again guaranteeing a 9.2, 9.3 as opposed to 9.1 ratio. This lag block is nothing more than a lag of the signal between the two by maybe 5 or 10 seconds, and that's what that's about. So again, some process controllers have a lag block in them. If you have to build a lag block yourself, picture a FIFO with a incoming and an outgoing number of variables. Let's say you collect the information every 1/10 of a second. So every 1/10 of a second you put one in, 5 seconds later, 50 variables later, you take them out. So basically you're just lagging that signal that's coming in and going out. Picture a rail car going into a tunnel, and then 5 seconds later or 10 seconds later it's coming out the other side. That's what we have here, is a lag block that you might have to build someday. And think of it as a FIFO, first in, first out. That's one way of doing it. It's not the only way of doing it, but it's one way of doing it. You can also build using the structural text language. You can do it as well using that. It's your choice. So also in the steel furnace, I ran into this, and this is a good example of using what I call tricks, or sort of things that you might not have thought about in order to get something to work. So in all furnaces, there is a pressure control loop. It's a slow acting loop, but as you're putting in, you have to take out. In other words, you have a fan up here and a damper that's pulling the air out. But you don't want to pull it out too fast, because what you're doing is you're pulling out heat. But you have to pull out some, because you're putting in some. You're putting air in, you have to take it out. If you don't let it go out, it's going to find a way out. It's going to find a way through the cracks or whatever to get the air to get out. So you have to let the air out. You have to let it go up the stack. But you want to be as conservative as you possibly can. So you want to have a slight negative pressure so that any flames in here stay in and they don't come out through any cracks in the sides. So you want to have a slightly negative pressure. In other words, you want to be pulling a little bit more, but not much, than you're putting in. Just a little bit. And that's a fairly slow acting PID controller, but it's a single loop controller, single little simple PID controller, fairly slow acting, that you have to put in. Every one that I've ever seen has this in it. You have to have it. What happens when the door opens? In this case, we were opening the door to put a piece of steel in, a slab of steel. What do you do? What happened? Well, as that happened, this upset this PID loop considerably. And what actually happened the first time, before we had the little fix in it, was the door opened, the flames rushed out, it burned the door up, it burned the door enough, it warped the door that had to be replaced. Not good. So you don't want to do that you don't have to replace the door every time you open the thing. So what did we do? Well, we put it in manual. The guy that was there with me, he said, all you have to do is to put it in manual, move the output, the CV, to a new variable, like 2% more than it was. How do you know 2%? Well, he just knew. But you had to move it to a new variable and then stick it back in auto. It'll take off and run up here. Instead of doing this, which is the way it was tuned to do, and take forever and burn the door up, you quickly move with that. So we had a limit switch put on the door, and as soon as the door was opened, or we said the limit switch open, we manual, put it up to the higher value, and then let it run at that variable. And it worked very, 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 very well. So again, this is not something that you would have known about or thought about from a book, but somebody knew how to fix this. And again, it worked very, 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 very well. So my point is this: you're the programmer. You sometimes are not the person that knows all these things, but you need to ask these kind of things from somebody who is familiar with some of the special situations, special conditions, and you'll figure them out. You'll learn them very quickly, and you might burn up a door or something like that, but in the process, you'll figure this stuff out, and it works very, 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 very well. So we also run into this idea of PID drawings. So every one of these processes that I've talked to you about had a PID drawing of some kind. And here is an example of that. Now, what are we looking at here? Well, we're looking at little circles, and the little circles have letters in them. They can also have numbers in them, but there's also symbology with these. Now you're good enough here that you figured this out, that this is a controller and this is a controller. How do we know that? Well, the third letter is a C. Third letter here is a C. The I, as it says the word indicator, and how do you know that? Well, down a little bit below this, we have some tables that actually tell you that. So FIC, what does that mean? Well, this is a flow. This is a flow transmitter, this is a flow controller. This is a flow controller as well. What does this thing do? Well, this is a transmitter that comes over to a flow controller. So we're controlling to a specific flow. What's the set point of this? We don't have any picture or clue here of what that set point is. If there's only one input coming in to this little bubble, this is a bubble of this thing, we know that the set point is from an external source, like on the faceplate. So in other words, you set up this signal from the faceplate. Here, we have a little thing called a multiplier block. So you set up a ratio between this one and this one, and you say, what is this? Here's primary and secondary flow. So this one has a flow, and this one has a secondary flow. That's a ratio of this flow. And that's what this PID does. So we take a percent of this flow, like 50%, 75%, 100%, 125%, or whatever. We multiply this flow times, and we bring it down here. This is our set point for this controller. You don't always see the word set, although they put it here in this case as a set point. This is the PV for this one, and this is its output. So this one has a flow, this one has a percentage of that flow. So whatever this flow is, this matches it to a percent. You say, is that guaranteed? Well, based on the tuning parameters, and once this changes, this one have to follow it and change to catch up with it. So this is a flow ratio controller. Here, now we talk about what I call pseudo programming, but it really is just a beginning exercise to start you to be able to write a PID program. And it talks about, we talk about basically identifying from a PID the controllers and matching up the set points, process variables, and the outputs to various devices. So here's a picture of a PID, and we go through it and we look at it and we try to set up these various blocks, and you can set them up vertically or horizontally, it doesn't really matter. But we look through and we see the various devices, and we see the inputs and outputs, we see lines, and we try to coordinate that with various blocks. So here's a example of a DIC, which is a density controller, DIC, density indicator controller, and it comes from a transmitter, and the input to that controller is the PV, is the PDT001, and that's this guy right here. So that is our variable for that. So our PID controller, this one right here, DIC, and we say PID is DIC001. Now, where does the set point come from for this? Well, there is no second input to this controller, so it has to come from an HMI, which we identify as SP, set point from the HMI. The output goes to the multiply block, so the CV goes to the multiply block, which is this block right here. The multiply block is, it takes this signal, it takes this signal and this signal and multiplies them together and becomes the set point for this block right here, which is our second FIC001. And the multiply block says multiply the value from this transmitter times the output from this PID block. What does this do? I don't know what this one does, but basically it controls, this flow controller controls this output valve right here. This was taken from a book that we talk about. It's the LibTech process control book, and it has hundreds of these drawings like this, and some of them you'll see that I just captured, the screen capture. This one I redrew, but this would be the answer to how to build the stick PID blocks from this picture right here. So you can follow the arrows. If there is a T, it's a transmitter, that's a process variable. The IC is controllers, DIC, FIC, those are PID controllers. The flow transmitter, that's a process variable, and then the valve is the output. So again, you have clues, and sometimes you have to deduce certain things, but basically from a PID algorithm, from a P&ID drawing, you can start the process of making up your blocks for your PLC. And again, this is just a starting point, but from these three blocks, if you get these three blocks configured correctly, you can take this and go to the field and try this out. And by clicking in the upper right hand corner, you can go between auto and manual and get these two configured. And then after that, you can add the modes. So what's not included in this program are the modes. So the modes are left out, but at least you get started. You can run it and you can see it running, and then you can add the modes, or you can add it all, have it all ready to go when you're basically ready to go to the field. But the idea of the beginnings of this would be take the P and ID, be the first thing I would do would be to put these three together. And after that, all you got to do is figure out all your other mode switching and your HMI and your alarms and all that kind of stuff, which are not implied here, but at least you've got a starting point to get the thing to run. Here's another example. And this is left for the student to do, but let's look at it here. We've got an FIC, that's a PID controller. Here we've got another one and another FIC, and then we've got a transmitter here, which is this is a transmitter. So this would be my process variable for this one. Where would be my set point for this one? Well, that would have to come from the HMI, and the output goes to this valve. Then we multiply this flow transmitter times a number, so that would be a multiply block, and that becomes our set point for this one right here. So this is a set point. Right here is a set point. This is our PV, or process variable, for this loop. And what is this? FSL. If we look back in our pages before, this is a switch, flow switch low, which sets an output that turns off this valve, hard turns it off, if this trips this low set point. In other words, we go below the low, it turns off this valve right here. It's a shut-off valve for this valve right here. So if you go too low, we're going to shut it off, and that's what this does. And that's part of your program. You would add that to your program. It'd be a compare statement. You say, well, how big do P and IDs get? Well, they get big, and these are some examples. I just took some pictures that maybe give you some ideas as to how big they get. They get very big and very complicated, but they're all based on something IC, something RC to get you started, and then you go from there. Most processes have a PID. Sometimes it's just implied. Sometimes you have to come up with the pictures yourself. Most of the time, the engineering staff sits up and puts a PID together, and from that they get the listing of the instruments. They get a listing of all the hardware that is needed, and from that they build their buy lists in order to purchase, and that also included are loop diagrams that actually show the wiring for each of these process control loops that we showed you before. So there's a loop drawing, a PID drawing, and then any electrical controls drawings which you would have on the PLC. That's how you put a system together like this. Other labs at school using Siemens PLC. So now we're going to go over to the Siemens side, and I've got a picture a little bit later of the ball in a tube, which we levitate a ping pong ball in a tube, and the feedback device for that is the laser, and the fan is the output that we actually modulate. So here's the laser, and it has a set point, an output set point for its distance. One of the nicest things about these is these lasers are very, very accurate and they're very, very high speed, so that they can actually control that level very, very well. Another one is a tank over tank, and this is a picture of that tank over tank where we actually are trying to control the level in the upper tank. Those are some early pictures. These are some later pictures, and they're being modified again. But basically, at this point in time, we set up with some pretty good sensors. The tank over tank, we've modified some of these sensors 2 or 3 or 4 times. So we started with a level control that was much simpler than this, but this one worked very, 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 very well. And this one's the one we settled on. So cheap isn't always the best. These are not cheap. These are like $200 a piece. But the level controller that we had before this did not work. So we used the Siemens PLC right here. And we also had a bilge pump in the bottom that pumped the water from the bottom up to the top. There's the bilge pump. There's the controller for the bilge pump. So this works off of 24 volts, and we have a 24-volt controller here, and it controls that speed very, 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 very well. This is that first low-cost sensor that we used for level control. Did not work. And this is the sonar controller that we use now for the level control in that upper tank. This is the first flow controller that we used. Notice the price, $12. Didn't work. It worked for about an hour and then stopped. This is the second one. This one worked up to a point, but the accuracy wasn't that good in the low end of the range, and it would stop flowing at about 25%. That does not work well for most PID algorithms, so we went ahead and bought another one. We bought this one. The difference in price is about $100. This is about $180. I kept asking, and finally we found this one as well, but we didn't use this one yet. But I would suggest, if you're building the system, to try to at least look at one of these. This is a $60 flow transmitter or turbine transmitter, similar to this one, but it costs a lot less money. Again, you continually are looking for the best sensors for your system, and that's notwithstanding, you're always looking for the best sensors. There's a third one that we did, or we're doing. It's a speed control of a DC motor, and I show you this one because this one was one that was in the lab for a while. It was mothballed because we couldn't keep these running. So this would be a DC control of this motor right here, speed control and position control. We settled on this little gear motor here, which we're using instead of with a analog control. This one had an analog control. We're using the digital control from the PLC. And with all these labs, they're all featured in separate chapters in the hybrid lab textbook. The hybrid lab textbook shows you extensively how to set them up and the programs involved. In this book, attempt to just begin the process and show you the startup, but not the whole gamut of how these things are controlled. So we had to kind of move all those to different chapters because this chapter just would have gotten way too big if we hadn't done that. This is another one, a tape rewind machine. And we've done this with both cloth tape and with string. So what we do here is we have an outlay reel and a take-up reel, and also this angled piece here in the middle is called a dancer roll with a potentiometer on it. And we've done various modifications of this. This is one of the good uses of 80/20, and we used it a lot to mount this and put this together. This is two PID algorithms. In other words, we control the speed here, we control the speed here, and we also use this to control the tension between the two so that we have a constant tension on the take-up side. And you can also put weights on this angled piece right here in order to make it more tense or less tense. And you can have the angle, control it to a specific angle of the tension. So this would be two PID loops here and here, and a third PID loop here to control the tension. Various ways of doing that. So why do we use Siemens instead of Allen Bradley? All of a sudden you see a switch from Siemens from Allen Bradley to Siemens. Well, we couldn't use the valve on the wall, and the Siemens system has some hooks, some analog values that we can create from the simple processor, the simple program controller that we have. Instead of having to use analog values, we can use digital values that we can read as analog variables. So again, we are talking about changing over from sensors that have analog input to ones that have just digital input, and especially with the little motors, those have encoders on them with pulses, and we can read those in through a high-speed counter, HSCs, and this shows how to do that. And we can take the outputs and put them through a PWM output, and we set those up, and those become pulse width modulated outputs, and those become analog values for our signals for the controlling of the output. So for instance, this would be a pulse width modulated output at about 75% on. This would be about 90% on. You can see the percentage of time that the output is on gives me an analog variable, analog value. It works very well for analog. And it's cheap, and it works very, very, very well in most of the applications that we have. In order to do that, you have to have a setup for each of these, the pulse width modulated control signal, and also the high-speed counter, which is shown here. The PID algorithm inside the Siemens PLC is not simple. It looks rather daunting, but it is not really that bad. You really only have to set up the K, the TI, and the TD. Those are the only three variables you have to do. And they even make it simpler than that, in that you do not have to even set these variables up. You just have to hit the thing called tuning, and it will set it up for you. So this is their equation. It's not that hard. If you look at it for a little bit, it's not that bad, because they have automatic tuning. Now, all of the PID that we've done in the Siemens is using the PID compact. We've not done anything with the three-step. We've not done that at all. It's just that all of them have been with the compact processor. And we've set them up pretty much similar to this. And again, I show these symbols and I show the setup screens in the other chapter in the lab textbook. So I'm going to go through this kind of quickly, but I'm going to give you some of the highlights as we go through this. Okay, so the one thing about the Siemens that is a little bit different is that you have auto and manual in what they call states. Now, if you look at the state list, there's 0 through 8. We only use, and we got away with this, and we don't have to do anything differently, the automatic and the manual. So you have to put, if you want to go to manual, you have to put a 4 in for the state. You have to put the variable, the PID variable state to a 4. If you want to go to automatic, you put in for the state a 3. And also with this one, you have to put in a change of state for you have to, in order to change the state, you have to do a one-shot to an input on the left-hand side as well. That's something that's new. They've added to the later PLCs, but you have to do it. So there's two things you have to do to the Siemens processor to get it to change state. 3 is auto, 4 is manual, and then you also have to toggle that bit on the left-hand side that says change state. So in your screens, you should have a screen like this, and this is a historical data trend, and you really do need this for analog variables. You can show this, and it does give you the ability to plot the variables and how they reacted, whether they're stable or not, and that's something that's very important. Here's a picture of the ball in a tube. Here's the ping pong ball at the bottom, and here is the laser at the top. There's a fan right under here, and you pulse that fan, and I showed you how that pulsing percentage PWM output turns this fan on a percentage of the time, and it levitates that ball at a certain height in automatic. You do not have to use this separate screen. If you want to, you can, but you can also use the screen of the computer as your HMI, but you have to have an HMI screen of some kind in order to make this work, especially for an operator. We've moved the cyclic time from 5 milliseconds. It was 5 milliseconds at one time, but this was the old way of doing it, but we've moved it to, I think, 50 milliseconds now, but we use the PWM output as opposed to this one. When we were doing it this way, we were turning the output on hard, either on or off, for that 5 milliseconds. So you would determine whether it was on or off, and for that 5 milliseconds, it would either be on or off. And that was one way of doing it. That's called a bang-bang controller, but you do not necessarily have to do that with this Siemens, and we found that out later, that you can use the PWM output and set it for 50 milliseconds or so, and use the PWM output, which gives you a much finer control than have to change it to an on or an off every 5 milliseconds. This worked, but it didn't work as well. So again, and the other reason is you don't want to do it this way is because every 5 milliseconds, you're calculating your PID algorithm, which takes time, and it takes a lot of your CPU time in order to do this. Not a good idea. You want to make this cyclic time 50 milliseconds or 30 milliseconds or 100 milliseconds as slow as you can so that you take the CPU and not burden it with that algorithmic calculation. But this is the way that this is the way it looks. So here is this. If you go to manual, you have to click this to enable the manual. This is the one. If you go to manual, you have to toggle this. And also the state is over here. You have to write to the state. Here's some of the screens that were there. And again, some of this has changed, but you decide how you want to write the program. I give you a starter program, and you can decide how you want to modify it from there. Okay, now, building of the faceplate. I showed you some faceplates earlier. Here's some faceplates again. This one is exactly, these are the exact ones that I showed you earlier. This is a more sophisticated one, but basically the same thing. A little bit more sophistication in it, but it still doesn't have the triangles that goes up and down 5% or 1%. Something you probably should consider. It's a little bit fancier. You decide how you want to do it. So this is the one that adds the 1 or the 5% to the set point or to the output variable. Here is a picture of a number of PID algorithms. Now, when we were talking about HPHMI, high performance HMI, they talked about this. They said, you don't need to show all that faceplate stuff, just this. And now, if you do this correctly, then you can look at all these PID algorithms by just looking at this right here. And what would you do if it went out of range or if it went off the rails? Well, you could have what we'd call an invisible button around it that you click on that area, and it would bring up a secondary or a pop-up screen, which would show you this, or it could show you this and the graphic, the the graph of the historical data of what it's been doing over the last 5 or 10 minutes, or last hour, or last 3 hours, or whatever. And that's what this is about. So you could have a picture of the process if you wanted to as well. You could have, in a more complicated process, you could have a number of these. More complicated process here, less complicated process. This works fine, but the invisible button brings this up, and then you can modify it, or you can do whatever you want to with it. But this tells you this information about this valve, and allows you to change it. Invisible buttons are very important. Tuning the PID block. Again, I mentioned a few variables for it. I mentioned about automatic tuning, but I want to show you that there's different equations used by different vendors. And these are the 3 basic equations. You can use any one of these 3, but what does that tell you? If you want to move from one vendor to another, what is going to happen? It's probably not going to work. You're probably going to have to redo your tuning parameters for your other processor and your other controller, and they probably will never work exactly the same. So you need to ask the question, which of these 3 do they do? Is it the same as the one that you were using before? And if not, what are you going to do about it? How are you going to guarantee that the response is going to be the same? That's up to you. But there are different ways of doing these, and just be aware of that. Bumpless transfer. What is bumpless transfer? Well, when I'm in auto and I have an error, I bump back to manual. But I don't want my valve to go to a variable that was set up for the manual set point. My manual set point was something that maybe was way off in space, maybe 0. You don't want your valve closing. You want it to be where it was before. So what you want to do is when you go from auto to manual, you want to stick the output, the CV, the output, to the manual set point. And that's called bumpless transfer. So you don't want things to automatically, when you go from mode to automatically whoomp, or whoomp, to go off the rails. So you want them to stay the same. This is something that may have already been written for you if you're doing a DCS system, but probably with a PLC system, you have to write this logic yourself, which basically means on a change of mode, a one-shot would move a variable from one. It would move it over to where it needs to be in order to keep the system running correctly. So you have to ask the question, what do I need to do to make this as smooth a process as possible? That's called bumpless transfer. Non-standard controller modes. Here, I introduce you to a non-standard controller mode called COT, or control output tracking. COT, or control output tracking, was nothing more than in chapter 15, we talked about a startup mode. Startup mode was keeping the outputs between the rails until you get everything up and running. That's important because on Monday morning at 5 o'clock in the morning, everybody's groggy-eyed from their weekend, whatever they were doing, and they're trying to start up the furnace or trying to start something up, and they need to keep the system between the rails. Well, you typically do not run an automated system at 10%, 20% of full on in auto. You run it in manual, so the valves themselves are set. And you cannot run a system usually at that low of a range because they're very unstable. So what you end up doing is you have the system in a mode that you'd call here, that I called control output tracking, which basically says start up zone 1, the valves go manually to a certain point. Start up zone 2, they would go to an advanced, they would move up a little bit, your gas in your air would move up a little bit, and you go to zone 3 where you're adding more. And then finally, when you've got all your zones running and you're stable, then you flip over to auto. Control output tracking looks like it's in auto, but it's really not. Your valves are in manual mode until you get up to the speed. Stay between the rails, stay between the high and low limits of where you're wanting to be, and you run in some kind of a manual mode until you get up and running. You can call it whatever. The people that I was programming this for called it control output tracking, but basically it's a special mode, which in this case was manual mode, but you lie to them, you say this is control output tracking. But basically, as you flip through the various stages, stage 1, stage 2, stage 3, you're basically opening up more of the valve manually to satisfy a certain amount of gas coming into the system. You can call it whatever you want to, but these are names that people have invented over the years for these other modes. And there's a lot of them. I don't know them all, I'm sure, but there's a lot of different modes. Loops within loops. So we haven't talked too much about one loop feeding another loop, other than through the PID, talking about those PID drawings. But many times, an output of one loop feeds the set point to another loop. And in the case of the ones in the lab, we have one. It's called the tank over tank. The output of the level loop, and the output of the level loop feeds the input to the speed of the bilge pump or the flow loop. So that's a loop within a loop. Well, what do you do in that situation? Well, basically you have an order in which you do it. You tune the inner loop first, okay? That's usually the flow loop. The outer loop would be the level loop. Tune that last. And one thing you want to make sure of is that the inner loop is tuned to respond faster than the outer loop. The outer loop should be responding slower. The inner loop should be responding faster. You can say this and remember it. It will be of good value to you. Inner loop fast, outer loop slow. If you do that, when you're tuning loops within loops, you probably have stability almost immediately. If you say the opposite, you will have instability almost immediately, and you will have problems. So basically, the tuning of inner and outer loops is extremely important, and that's how it's done. I talk here a little bit about you're going to run into people that are going to say DCS is better than PLC. And other people say PLC is cheaper and they're therefore better than DCS. What are the differences? Well, with a DCS system, if you change one variable, you've changed it in all aspects. You've changed it all across the board. With the PLC, you have to be careful because the alarm may not be changed if you change the control or if you change the HMI. You've got three areas. You've got the diagnostic or alarm area, you've got your control area, and you've got your HMI area. And they all three have to be changed if you make a change in one of them. So you have to be careful. You have to realize that, and you have to move together. Sometimes maybe you can put variables together so that you can do that automatically, but it's nice if you can, but many times you can't, and you have to guarantee that if you make one change, you make it across the board in all three areas. That's why DCSs people argue that they're more sophisticated and better, because you don't have to worry about that. You just make the change one place and you've automatically got all those changes ready for you. Also, they take care of the idea of how often to read the inputs and make sure that the inputs are the freshest and up to date, as opposed to you having to worry about scan rates and all that kind of thing. That's something else that you have to be aware of and take into account as you're getting your cards ready and all that kind of stuff. Redundancy, all those kind of things. The list is right here. You may have to work through these to find out if there's any reason why you would want to go to DCS system. But if you want to have a taste for DCS, just flip over and write your program in FBD. Function block diagram in FBD looks very similar to DCS programming because they are the same. So if you look at FBD programming in the PLC, you basically accomplish the same programming style as done with DCS. If you ask the question, what do I need to do to make a more sophisticated controller than a PID controller, what would you look at? Well, one of them is the Kalman filter, and there's others, but basically the Kalman filter is a beginning down this road of multiple inputs, multiple eyes, and being able to control multiple outputs from an algorithm. So basically that gives you an idea of this. Yes, you can do that. And if you want to get involved with that, there's some spots here that you can click on and try, or others, but try Kalman filter and away you go. Okay, so here are some of the other labs that I have and where they're featured at. In chapter 21 of the labs textbook is the gear motor speed control. Chapter 22 is the ball and tube. Chapter 23 is that tape rewind. And 24 is the valve on the wall. And 25 is the tank over tank. And we continue to modify those as we continue to update and get more sophisticated with each of those labs. Here's the labs that I described at one time, but you may decide that you want to go back and you want to do one of these labs as well. These are the less expensive labs. The only one that here that is very expensive, the valve on the wall is the price of the equipment that I have, plus you have to have a good drain. Ball and tube is not very much money. The tape rewind is not very much money. The gear motor speed control is not very much money. The tank over tank, you may end up with a fish tank over a fish tank, or you may end up with something else. But our setup cost $1,000 for that plastic system. So that was the most expensive part, plus then the $200 for the level control, and then the $180 for the flow meter. That's it, and the PLC of $180. So you can decide which way you want to go on that, but the tank over tank is $1,000 for the plastic, and that was probably the most expensive part of that, and it did cost quite a little bit of money, but that's not as expensive as some of the other systems that you might tie into for that. Okay, we come down here to some of the questions at the end, and I'm going to go through these rather quickly. Most of these I've answered already in the lecture. Very good questions. They're answered in the chapter. Okay. This lag controller, again, using the FIFO block, or you can build it with the structured text language. Either way, we did this lab. We did this one in our lecture. We didn't do this one. This is the same, except there's all these low and high alarms over here, which is basically not hard, but that's all this is alarms. This had to do with cyanide, so you want to make sure you get this one right, or you're dealing with cyanide gas, which is not good stuff. So again, can be dangerous, but get it right, it's going to work. Okay, a discussion comparing ECS and PLC. Here is an article that was a discussion about that, and you may decide to read that through. Here's another example of this one, there was an equation that was given. So in this case, there was a model of an equation that actually was given to do this right. But you have to plug that in into a compute block or calculate block. And here's the one where we turn it to manual, turn it back to auto for the so the flames don't escape. And here is the problem for the tape windup, the windup of the tape, the beginning start of that program. And again, this is found in the chapter in the lab text as well. A group built this in their capstone project this last semester in capstone. They use this, and they use a robot to put the tape on, and then or to put the winder of the thing on, and then they wound it up, and that was it. This is being remodeled over the summer, and we're putting in new flow meters in each of these. So these are going to be gone. This will be gone. This will be gone, and we remodeled these a little bit. But these basically are very sturdy devices, and they're very handy. 5 gallons in the top will get it close enough to the top that you can actually make this thing run. Very stable process. You cannot make this go unstable hardly at all. But again, a loop within a loop, you can make it go unstable if you tune it totally incorrectly. And we're done.